Question 16, chromatic number. Jordan drew the following conclusion. The greater the number of vertices in a graph, the greater the chromatic number of the graph. Is Jordan's conclusion true or false? Well, it sounds reasonable until you actually think about it. I'm saying it's false. The chromatic number is about the connections between the vertices, not about the vertices. You could have a graph with 6 unconnected vertices, and your chromatic number would be 1. But let's look at something with just 2 vertices. So A, B. They're not connected. Chromatic number? 1. Let's look at another AB. This time I'm going to connect them. If the A is yellow, the B can't be yellow because they're connected, so I'm going to make that a different color, blue. This chromatic number would be 2. It doesn't prove or disprove our theory, but what it shows is that I have a greater chromatic number without changing the number of vertices. Let's change the number of vertices and see what happens. Here I have 6 unconnected vertices. If I paint the A yellow, it's not connected to the B, so the B could be yellow, and the C could be yellow, and the D and the E and the F could be yellow. So this has a chromatic number of 1 because they're not connected. So this actually proves Jordan's theory wrong. Jordan is saying the greater the number of vertices in a graph, the greater the chromatic number. But this one has 2 vertices, the second one has 6 vertices, and they both have the same chromatic number, which totally disproves Jordan's theorem. Here, if I connect the A to the B, to the C, to the D, to the E, to the F, let's pretend that's F. Notice our chromatic number, like A, yellow. Now B is connected, so it can't be yellow. Let's make it blue. But C can be yellow because it's not connected to A. And then D would have to be blue, then E would be yellow, and F would be blue. This has a chromatic number of 2, but it has more vertices than this. The more vertices, the greater chromatic number of the graph? No, untrue, totally untrue. And by the way, if we connected everything to everything, if I connected every vertex to every other vertex, my chromatic number is equal to my number of vertices. A is connected to B, so it has to be a different color. And B is connected to C, so it has to be a different color than B, but it's also connected to A, so it has to be a different color than A or B. So I made it red. And then D is connected to C, can't be red, connected to B, can't be blue, connected to yellow, can't be yellow. So I made D green. E, connected to everything, has to be a different color, can't be yellow, can't be blue, can't be red, can't be green, so it must be white. E is connected to everything, can't be blue, can't be yellow, can't be blue, can't be white, can't be red, can't be green, so I picked purple. This one has a chromatic number of 6. That totally disproves Jordan's conclusion. So number 16, false. And that's it for number 16, and that's it for the exam. Have a good day.